chaos, randomness, disorder. These might not be the first things that enter your mind when you think of a carefully controlled laboratory experiment, but randomness seems to be all around us, ever creeping into systems of higher order. Rigid mountains chemically weather, becoming dissolved minerals dispersed across rivers and oceans. Plumes of water vapor from smokestacks diffuse into the surrounding atmosphere without any apparent trace. Materials just seem to naturally want to spread out. Last time, we took an in-depth look at how heat flows during chemical changes. We saw how early physical chemists like Joule and Berthelot focused on simple systems in which no work was done. And this allowed them to begin to crack the code of how energy flows during bond formation and breaking by measuring heats of reactions in calorimeters. The early focus on heats of reactions, as you might expect, led to an overemphasis on its importance in determining whether a chemical reaction is expected to happen. It was a long and widely held belief among chemists that in order for a reaction to happen, it must be exothermic, or heat-emitting. But there are many processes that defy this rule. Rapidly expanding gases actually get colder, yet open the valve on a can of compressed air and the air expands anyway. Put a few drops of water on your skin and let it evaporate. You'll feel a cooling sensation as the water absorbs heat energy from your skin, becoming water vapor. So there was something missing in the paradigm of this day. Clearly, systems had a tendency to change in ways that release heat. But it's equally clear that there were many exceptions to this rule. All of these exceptions pointed to a second force pushing chemical reactions forward, a force so powerful that it could sometimes trump the influence of heat. But what was it? The answer to this burning question begins with an Austrian-born physicist by the name of Ludwig Boltzmann. In the 1870s, as a young professor of mathematics, Boltzmann began to formulate a theory that would ultimately prove to be the final piece of the thermodynamic puzzle that explains why and how chemical systems change. He accomplished this not by focusing on heat, but on disorder. He stopped to consider just how disordered a particular system is and wondered if somehow a mathematical quantity could be assigned to indicate its level of disorder. Now that might seem a bit odd. After all, isn't random an absolute term? Something's either random or not. Well, not exactly. We know from experience that matter behaves in very predictable ways. The gas in a balloon will always fill the balloon completely. The liquid water will always take the shape of the container that it occupies. A block of iron like this one, fashioned into the shape of a skillet, will retain that shape indefinitely. So, at a glance, it seems like the air in the balloon, the water in your glass, and the iron making up a skillet are unchanging, in exactly the same configuration from one time to the next. If you inspect it at one moment and then another, they appear to be the same. These states are called macrostates. They're a description of the material at the scale that we commonly encounter and understand them. But the macro scale was not the focus of Boltzmann's ideas. Boltzmann was concerned with the predictability of a system at the molecular and atomic level, what we call the microscale. Remember that those samples of air, water, and iron contain billions upon billions upon billions of atoms and molecules, each of which can move, rotate, and vibrate. So there are a huge number of potential positions and velocities for each atom and molecule in these objects at any instant in time. If we had a molecular camera that could photograph these objects at that level, taking pictures of them at different times, we would see atoms and molecules in differing positions, moving and vibrating in different ways each time. Boltzmann called these states, the ones that consider the position and motion of every atom in a system, microstates. And as you might imagine, there are sometimes many, many microstates that can accurately describe any one macrostate. Let's consider a simple example of a process to better understand what Boltzmann was trying to get at. Consider just about the simplest system that we can, one that has just two particles in it. And those two particles can each be in one of two places. In this case, I've created a little box here, where my particles can either be on the left side of the box or over here on the right-hand side of the box. Now, assume that they can only be in one of those two states and that they interconvert at differing speeds or randomly. When that's true, let's start this thing in motion here and see how long we have to wait to find this system in an ordered state with both particles on the same side of the box. Well, it shouldn't take too long, right? At this moment, they're going, oh, there they are. Oh, now we're ordered again. As you can see, it doesn't take long before we reach the situation where these particles are on the same side. And that's because in this system, with just two particles and just 2 microstates each available, we have a situation where there are really only 4 microstates for the whole system. That is, 2 microstates which describe the system mixed, and 2 which describe the system as being completely ordered. So it didn't take us too long, did it, to find a snapshot in time where the system was very, very ordered. But what if we graduate to something slightly bigger? Let's do 4 particles this time. Again, randomly interchanging between the 2 different states. Well, once they get to being mixed up here, it takes a little while longer before we can catch them. Sure, we can get them if we wait long enough, but it's a little more challenging to find a snapshot in time where all 4 are on the same side. Now, the reason for this, Boltzmann would argue, is because the number of microstates that describe a highly ordered system have decreased relative to those microstates that describe it being mixed. Specifically, we have 6 microstates which describe complete mixing, 8 microstates which describe partially mixed, and only 2 which describe completely ordered systems. So just by going from 2 particles to 4, we can already start to see a shift in the system towards having more possible configurations that we would describe as being random or mixed. If we graduate to an even larger system, say 6 particles, it takes us even longer before we're able to see this system in a very ordered state. And that's because, of course, the number of microstates, again, are changing in favor of randomness. Here we've got a situation in which we've got 20 microstates that describe a thoroughly mixed system, 30 microstates that describe the system being mostly mixed, 12 that are fairly ordered, and only 2 in which we have a completely ordered system. Again, we're getting more and more and more microstates that describe mixing, relative to fewer and fewer and fewer that describe order. If we continue this, we would find that this effect continues onward. We have 8 particles, 16, 32, and even 64. If I were to run all of these, we would have to wait for quite some time if we ever see the 64 particles on the same side of the box. It's very unlikely to happen at all. And that's because the number of microstates accessible to these is changing. Now let me overlay these so we can see them a little bit better, and it'll be very clear. Notice that when we align them, that those microstates that reside in the middle here, that we might call disordered, are growing in number relative to those over here on the outsides that describe what we would call a very ordered system. Now, we just looked at about 4 to 64 particles with only 2 potential states each. Now try to imagine a mole of particles that can be twisting, vibrating, rotating, and moving. There's quite a number of microstates available, and this becomes a situation where it's practically impossible to observe a system that is completely ordered. This is the essence of entropy. The macrostate of any collection of atoms or molecules can be consistent with any one of a vast number of microstates. Just like the degree of mixing in our simple example can be consistent with any one of many arrangements. Boltzmann formulated a famous equation that relates the randomness of a chemical system to the number of microstates accessible to that system. And the number of microstates can be genuinely staggering. Boltzmann's famous equation is remarkably simple. It only consists of 3 terms. The randomness, or entropy, which we usually designate as S, being equal to Boltzmann's constant, K, times the natural log of the number of accessible microstates. This allows us to either take the number of microstates and from that calculate entropy, or, more interestingly sometimes, determine from the measured entropy of a system exactly how many microstates it has accessible to it. So let's do a simple one like that right now so that we can get our heads wrapped around just how monstrously large this number can be. Let's consider 1 mole of water in the liquid phase, just 18 grams of water, enough to fit into a shot glass. Now, the entropy of that liquid water is 69.95 joules per Kelvin. So that 1 mole of water has that entropy associated with it. But what does that really mean? How many different microstates are there for that 1 mole of water molecules that are moving, rotating, vibrating, and colliding with one another? Well, to determine this, we simply use Boltzmann's constant and multiply that by the natural log of that number of microstates. So I've got an equation here with a single unknown, W, so I can determine it. I'm just going to divide through by Boltzmann's constant so that I can cancel. And I get 5.07 times 10 to the 24th is equal to the natural log of the number of accessible microstates. Now, 5.07 times 10 to the 24th might seem like a really large number, and in fact it is. But in order to undo the natural logarithm here, I've got to raise e to an exponent of that size. So this number is not the actual number of microstates, that's just the exponent in the number of microstates. The actual number of microstates works out to about 10 to the 2.2 times 10 to the 24th. That means that if I were to look at this number written out, passing by my screen at about this speed, I'd have to stand here for 1,000 times the age of the universe simply to watch the number go by. So Boltzmann's new entropy calculation allows us to determine just how disordered a system is, based on how many microstates it can adopt. Combine this with nature's clear preference for disorder, and you have a way of determining how systems left to themselves will change through time. Of course, they'll trend toward disorder, because there are simply more microstates consistent with that macrostate. Left unattended, a house of cards is destined to become a disordered array of cards on the floor. An ordered wall is destined to become a disordered pile of bricks. Even ordered mountain ranges, some of nature's mightiest creations, are ultimately destined to become disordered beds of sand on a river delta over millions of years. Now, in the spirit of our course, let's scale that analogy down to the level of atoms and molecules and apply Boltzmann's thinking to those systems. Remember that Boltzmann's theories hinged on atomic theory being true. In this case, gases should consist of extremely small, fast-moving atoms or molecules that move randomly, colliding with one another and the walls of their container. With that in mind, picture a system like the so-called neon lamps from our earlier discussion on the electronic structure of atoms. Most of these lamps actually contain not just neon, but a mixture of gases. So let's say that I have a tube in which I have two different gas samples, one helium and one neon. Boltzmann's theories tell me that these molecules are moving in random directions and speeds which vary statistically. So they're isolated from one another by some imaginary barrier. So right now, the two gases are separated in space. And this is a highly ordered system. Helium is on the left, neon is on the right. But when I remove the barrier, the random motion of the gases causes them to mix. Ultimately, after enough time has passed, the two gases are clearly evenly distributed within the total volume of the system. As the system progresses from one microstate to the next, we can see that at no time do the atoms reach a state in which they are perfectly separated as they were in the beginning. In this graphic, I've used just a few dozen atoms to illustrate my point about microstates. Now, picture this if you can. A neon lamp bulb like this one contains somewhere around 1 billion trillion atoms of gas, about 0.02 moles, each of which is moving independently and randomly. It all adds up to a mind-bogglingly huge number of potential microstates, most of which accurately describe the macrostate of having the gas molecules distributed evenly within the volume. But what are the odds that without any outside interference, purely by chance, out of 1 billion trillion atoms, that all of the helium atoms from the sample will be found on one side of the tube and all of the neon on the other, even for an instant? Boltzmann would argue that the odds are practically zero because so few microstates describe that macrostate. We could wait and watch for another 5 billion years. At that point, our sun would extinguish, our solar system would die, and we would still have never seen this happen because we are waiting for one just vanishingly small proportion of microstates to occur. If you need evidence of this, you need look no further than one of these lights in action. If the gases were not intimately mixed at the atomic level, then the color of the tube would not be uniform. Yet, no matter how long you wait and stare, the tube will always glow the same color along its entire length, showing that the gas atoms inside are always thoroughly mixed. All of this leads us to the second law of thermodynamics, which can be stated in any number of ways, but essentially states that entropy, or randomness, in a closed system tends to increase unless it's countered by an input of energy from an outside source. Put even more simply, the universe is always becoming more random. Any homeowner can attest to this simple principle. Just like the house of cards, a wall, or a mountain, if left to reach its own lowest energy state, a house will eventually crumble into a disordered pile of rubble. So how do we prevent this change? Well, significant energy must be put in by the homeowner to keep the system in its desired macro state. This is because there are far more microstates consistent with that unattractive pile of rubble than there are with a beautiful home. So every time you clean the kitchen, patch the roof, or mow the lawn, you are fighting entropy. It's a battle that you can continue indefinitely, as long as you have an external source of energy. In this case, that source is you. This is particularly disconcerting from a cosmological perspective, since cosmologists often think about the entire universe as one gigantic closed system. If we think in this way, Boltzmann's equation and the second law of thermodynamics make a dire prediction: that the overall randomness of matter in the universe will constantly increase until it simply can't anymore. Since, in theory, there's nothing outside of the universe to act as a source of energy input, we're doomed by the second law of thermodynamics. This manner of thinking leads to the prediction that someday the universe will become completely randomized, a slave to the second law of thermodynamics. Its entropy will continue to grow and grow until the whole of the universe is one single uniform temperature. At this point, there will be no available energy left to power life, planetary processes, or even the vast engines of stars. Cosmologists call this phenomenon heat death. And if it's our destiny, then the only consolation is that it's going to take the universe billions and billions of years to get there. So we still have time to finish this course. Boltzmann's method of modeling entropy with microstates has ultimately proven to be correct. During his day, atomic theory upon which his equation hinged was still being hotly debated. It would take a few more decades and the support of one of the most revered physicists of his own day, Max Planck, to finally make Boltzmann's ideas stick. Nonetheless, Boltzmann is popularly given the credit for recognizing the connection between entropy and microstates. It's also worth mentioning that although Boltzmann gets the lion's share of the credit for this concept and a very chic inscription of the equation on his grave marker in Vienna, it did have other advocates, including Lord Kelvin, whose famous temperature scale is validated by Boltzmann's equation. As happens so often in science, in this case, individual accolade fails to capture the spirit of community that truly brought about this revolutionary concept of entropy. So, by now it should be clear, Boltzmann's ideas about what we now call statistical thermodynamics were spot on. Nature gravitates towards randomness. Another clever way of stating this concept is that nature abhors a vacuum. In short, solids would rather be liquids, and liquids would rather be gases, since each has consistently increasing degrees of disorder or entropy. We can use this general rule to our advantage to help us predict when certain reactions will take place by considering how entropy changes as the system converts from its initial state to its final state. Before we do this, though, let's consider a few different sorts of substances and try to determine which is likely to have the greater entropy compared to the other. How about 1 mole of liquid water at room temperature, which occupies less than a square inch, compared to 1 mole of water vapor at the same temperature? That's 22.4 liters worth. Both have the same number of molecules, but which has the greater entropy? Of course, the molecules in the water vapor are moving faster across a larger volume because they're in the gas phase. Meanwhile, the molecules in this liquid sample are more confined in space, able only to move, shift, and vibrate within the confines of their specific location defined by the volume of the liquid. Naturally, more microstates exist to describe the water vapor. So we would say that the vaporization of liquid water has a positive entropy change associated with it. This helps us to explain why a glass of water left out on a counter long enough will evaporate and fill the room with water vapor. In the vapor state, more microstates are available to the water molecules. So the second law of thermodynamics predicts that it will evaporate if given enough heat energy. So a pure substance, as a gas, has a greater entropy than does one as a liquid. And by extension, a liquid in turn has a greater entropy than the solid. This is because molecules in a liquid at least have free run of the volume that liquid contains. In a solid, by contrast, molecules are stuck in a fixed location, able only to shift and vibrate, but not to move freely within the volume of the solid. The same general hierarchy of entropies applies to chemical reactions. When we want to analyze how entropy drives chemical reactions, first and foremost, we have to look for gas formation or consumption, because atoms and molecules in the gas phase drastically increase the number of accessible microstates for a system. Determining whether entropy is increasing or decreasing in any given process is actually fairly straightforward. Let's take a couple of examples here. Let's look at the reaction again between propane and oxygen that we've come to know so well. In this reaction, we balanced it out to find that we have a grand total of 6 moles of gas reacting to form a grand total of 7 moles of gas at the end. The reaction stoichiometry helps us to predict that the number of moles of gas is going to increase as this process takes place. Well, what does that mean about entropy? Well, remember, gases like to have lots of space. Their particles move very fast and very randomly. And so gases always drive entropy in systems when they're present. So in this case, the fact that we've increased the number of moles of gas as the reaction has gone forward tells us that entropy is increasing as this reaction happens. In other words, delta S is positive. Now consider our second reaction, in which we have hydrogen gas and oxygen gas reacting to form H2O, water vapor. Now in this case, I've got a total of 3 moles of gas in my reactants. Right? So if I'm going to have a reaction with a positive entropy, I've got to have more moles of gas than that. But in this reaction, I've only got 2 moles of water. So in this case, the product had fewer moles of gas than did the starting materials. And because we've decreased the overall amount of gas in the system as the reaction progresses, we could predict that the entropy of this system is decreasing. Delta S for the combustion of hydrogen is negative. But just as with enthalpies, sometimes we need more than just a hunch about the overall sign of entropy change associated with a given system. We need an exact numerical value for the entropy change. We'll see in our next lecture why this is so very important, but for now, let's just focus on how we can get the number that we need. Just like enthalpy, entropy is a state function. But unlike enthalpy, entropy is absolute. So we can go to a table and find the experimentally determined molar enthalpy for any material that we choose. The standard molar entropy of a particular compound will always be the same, no matter how it was formed or what conditions it's experienced before. And just as this allowed us to determine standard enthalpy changes for reactions from tabulated data last time, it again allows us to do the very same thing for entropies today. So let's test our earlier hypothesis that the entropy change for the combustion of propane should be a positive number. Well, now we know how to get the actual number, so let's do that. Again, our balanced reaction for combustion of propane. What we need to do is calculate the total amount of entropy that the system loses when a mole of propane and 5 moles of oxygen gas are consumed. Then calculate the total amount of entropy gained when 3 moles of CO2 and 4 moles of water are produced. So we're going to go to the tables and find out what the standard molar entropy of propane is. It turns out that that is 269.9 joules per mole Kelvin. And I multiply that by 1 mole because my reaction stoichiometry tells me I'm dealing with 1 mole of propane. I'll go back to the tables and do the same thing for oxygen. 5 moles of oxygen are going to be consumed, and each mole is going to give up 205.0 joules per Kelvin of energy. We'll do the same thing for those products that we're making. we're going to add the entropy gained from the CO2. That's going to be 3 times its standard molar entropy. And for water, of course, 4 times its standard molar entropy. Now all I need to do are combine all of these terms mathematically, keeping a very close eye on those signs, making sure that I'm adding entropy for my products and subtracting entropy for my starting materials. And I can determine that overall, the entire system is going to lose this much entropy as the products go away. We're going to gain this much entropy as the products form, giving me a grand total of plus 101 joules per Kelvin for this reaction. So our tabulated values and calculations have validated our original prediction. Indeed, the entropy change for the combustion of a mole of propane is positive. Not only that, it's positive 101 joules per Kelvin. We now have a number that we can use for the entropy. So let's summarize our discussion from today. We started by thinking about randomness and some examples of naturally occurring processes that proceed with an increase in disorder. We discussed the second law of thermodynamics, which can be encapsulated by the statement that entropy of closed systems always increases. We met Ludwig Boltzmann, who helped us to put an equation to entropy by thinking about disorder as a function of the number of microstates that describe a particular macrostate. Next, we saw how we can easily predict the sign of entropy changes for most reactions simply by looking for gases and, in some cases, solutions on either side of the chemical equation. Finally, we explored how we can use absolute entropy values from tables to calculate the expected entropy change for any chemical process that we can imagine. So, in our last 2 lectures, we have covered enthalpy, or heat, and entropy, or disorder, in relatively simple systems. We've seen how each of these 2 properties drives chemical change, with exothermic reactions being favored, as well as those creating more disorder. But one burning question remains. What happens when enthalpy and entropy are at odds? How do we determine who wins? Next time, we're going to put enthalpy and entropy together and learn about an equation that can account for both of these reaction-driving forces simultaneously. Gibbs free energy will be our topic next time. And we spent quite a bit of time during this lecture looking at how to put a numerical value to entropy changes in processes that go on in the chemistry lab. But if you've got a keen eye, you can notice changes in entropy taking place all around you in nature. So this challenge problem is designed to get you thinking a little bit more about that. Here's our question. Consider the following systems and ask yourself, in which of these processes is entropy increasing and in which is it decreasing? I've got 4 for you right now. Ice within a glacier melts in the summertime. What's going on here? Well, glaciers consist of fairly pure ice, solid water. And of course, the process of melting creates liquid water, in which those molecules are no longer locked in place within the matrix of the material. They can move freely, tumble, and slip past one another. This means more potential microstates, which means an increase in entropy. Dissolved sodium chloride in seawater can be deposited as a mineral called halite, or rock salt. When this happens, those ions that were free to move through the entire body of liquid water are now confined within space in a solid. Therefore, the entropy in this case has decreased. The air inside of a hot air balloon as it's heated. Now, what is heat? Heat's the motion of molecules. And so as you heat molecules and they begin to move faster, they have more potential speeds at which they can move. In other words, they have more microstates. So the heating of a material like this would constitute an increase in entropy. Finally, moisture condenses from the air to form dew on a blade of grass. Condensation of moisture from the atmosphere is a very important process in driving the chemistry of our atmospheres and our environment. But in this case, if we think just about that water that's moving from the air in the gas phase to being confined into a very specific volume in the liquid phase, that particular system has entropy which is decreasing because there are simply fewer available microstates to a droplet of dew than there are to a cloud of water vapor.